I got this way. I'm not sure what the ratio of like slight fever to Mountain Dew is, but this is my third, so I'm just going to try and get it done. So homework. How's homework going? Let's see, who was talking to me about data? Is that Lindsay? That was you? Okay. Should we talk about data and how to make variables? So in this homework, I'm asking you to use group mean centering, which, if let's pull up, let me see here. It will look in structure a lot like what you did for homework 3. Here's an example that homework 3 used where we were doing between and within person mean centering, which is the same thing as group mean centering. So once you have your cluster level 2 means for stress and coping merged into your data set, at that point you can center your level 1 predictors around them. So the code would look like this in structure, where you'd be creating a within level variable, which is the original person level variable minus the original cluster mean. So don't use the centered version of the clustered mean that's centered at 5, use the original. So then you would end up with 3 predictors that are level 2 cluster level things, years of experience, which is already in your data, centered at 5, the center level, group level, level 2 coping, which you will then center at 5, and center level stress, which you then center at 5. So then you have the within center coping and stress variables to be created using the original variables minus the center means. So yes, terminology in this case, level 2 is the center that these people go to, the treatment center group. You can think of it that way. So groups are 2, people are 1. So we have between and within, same as usual, but it's between and within group, where within group is the same thing as person in this case. Just to remind you, if you get the right -2 log likelihood, you have the right model. But once you have level 1 random effects, they are not equivalent anymore. And so it will matter at that step, whereas it may not have mattered previously because of the way that you added things in the models. Once you group mean center your level 1 predictors, not at 5, but at the center's mean. Like up to this point, if you've been centering at 5, you could have gotten everything right because you're just swapping out contextual effects for between effects. But once you have it being random, then it is not an equivalent model anymore. It'll be close, but not exact. Not exact enough. So yeah, that will matter. What else? Nope. Okie dokie. Well then, let me know if you come up with anything. This is due Monday. And we were talking about generalized models. Something is blinking on my screen yellow and red, and I don't know if that's good or not. Now it's green, so that seems better. I guess we'll find out after class. My laptop is, for whatever reason, keeps dropping the internet, so I don't know what's happening, but I'm trying to stream. I really am. I promise. So tell me what you remember from last time. Let's start with vocabulary. What does generalized mean as opposed to general? The DV does not have normally distributed, what we used to call residuals, and now we're calling it conditional distribution. So it's for data that aren't ever going to be normal. Not data that you could transform plausibly to get to normal, but things that are never going to be normal, like binary is the first example that we're going to do. What's a link function? Or give me an example of a link function. We'll start there. Logit. Give me a synonym for logit. Log odds, yes. I would also accept as a third pronunciation, remember from last time? Log it, because you take the log of it, and therefore it is the log it. If you have something like a count of events, you can't have negative counts. So that ranges from 0 to positive infinity. So these are all instances in which the prediction from a linear model has to understand that it needs to shut off at one end or the other or both. And link functions do that. So we talked about logit, which is the log of the odds of the probability of a 1. And it has a 0 point at a probability of 50-50, which corresponds to an odds ratio of 1. So logit of 0 is an odds ratio of 1, is a probability of 50-50. Negative logits mean that you are below 50%. Positive logits mean that you are above 50%. But a logit can keep going forever and ever. It ranges from positive to negative infinity, which is why we can predict it with our linear model. A line can keep going in logits. When you back translate the predicted logit into probability, the probabilities stay between 0 and 1 like they're supposed to. So that's why we can use logits for binary outcomes as well as for proportion correct types of outcomes, because they still work within that spectrum. Give me another link function. Probit. Yes, that one is also known as ogive in the world of IRT. What's a probit? Cumulative probability, yes, it comes from the cumulative normal distribution. Probit is a z-score. It's the z-score that goes with your probability. Do you remember back in intro stat when you had like tables in the back of your textbook? Maybe I'm that old. You guys probably had the internet by then. I did not have the internet when I was taking intro stat. It was like a brand new thing. But we had tables in the back, right? And you look up your probability and you get your z-score, or you have your z-score and you look up your probability. It's that mapping. So a z-score of 0 is the same thing as a logit of 0. It does the same type of mechanism. As a z-score goes from negative to positive infinity, can be predicted by a linear model. But when you back translate it into probability, the probabilities stay within the bounds they're supposed to. What is it called technically if I say back translate? I also say unlogit. That is not how you would talk about it in a paper. Inverse, that's the inverse link. The inverse link function is what takes your logits and puts them into probabilities. The link function takes your probabilities and puts them into logits. And the formula for this is all over your notes, but I'll just do it again here. To go from probability to logit, it's the log of a marker that doesn't work, log of the odds, which is probability over 1 minus probability. That's how you go from probability to logit. To go back again, it is e to the logit over 1 plus e to the logit. As the closer you get to 1, the variance around it necessarily has to shrink, and the closer you get to 0, so does the variance. But transforming probabilities into logits, it doesn't know that it's supposed to do that. It's the combination of the logit link function and what's going to be a binomial conditional response distribution. That's what's going to allow it to take the error and change it as a function of the mean, because error is determined by the mean in this kind of data. So it's not the same thing to transform your probability into a logit and then analyze those logits using a normal model. Now, I have done that before, not just you. I've done that as recently as like this month. I've done that for measurement models. I don't know of any software package that you are allowed to fit a latent variable structural equation type model that has a binomial link function, including M+. So I said, all right, go ahead and take your probability, transform it into a logit, and stick that in your model. Because then at least you're solving the line problem, the fact that the line needs to shut off. that you need a nonlinear relationship between your outcome and your predictor. The logit solves that problem. The binomial response distribution that goes with it solves the error variance problem not being normal and not having constant variance. So it's two things that go together, the non-normal conditional distribution and the link function. All right. So by the way, all of this that we're talking about, this completely replaces non-parametric statistics. You need a class on non-parametric statistics like you need a class on how to program your VCR. I'm just saying. That's what people used to do when they had non-normal outcomes. They have to type both of these things. You could type one or the other, and the other option will be invoked. But that's all you have to do is change your link function to make sure your predictions stay within the bounds of your outcome, and change the conditional distribution to one that would better describe it. Otherwise, all the tools that you learned already about linear models are going to apply. All right. Questions on any of that before we jump back in? What about dependency? What's dependency again? Correlation. It's either a problem to be solved or the whole point of your study, depending on one's perspective. The fact that you have longitudinal data means you have dependency of observations within a person. Or if you have cluster data, you have dependency of persons within a group. Does anything that I've talked about so far today handle dependency? Link functions, alternative distributions? Nope. What do we put in our model to handle dependency? Meaning to predict that certain observations are related to each other because of their sampling. Starts with an R. Random effects. Yep. So if your observations are not independent, that's what random effects models are for. So we're combining everything that you've learned thus far, how to handle dependent data, broadly construed, and now model like a logistic regression to a multi-level equivalent. So what could you call it, by the way, that someone will know what you're talking about? What if you have dependent data, but you have a binary outcome? You could call that a multi-level logistic regression. That would be fine. You could call that a generalized linear model. You could still call that a multi-level model. So you can pick a lot of terms that will make it understandable, but those are the ones you want to hit. Make sure you mention the multi-level part, meaning mixed, and the fact that you are going to be using a link function and some other distribution. So if you say logistic, people will know that you mean logit-Bernoulli combination, but it never hurts to be explicit. So in the write-up that I have, I have a little paragraph that describes that you can feel free to borrow for your own use later on. So are adding in random effects. Now, remember my whole, like, once upon a time there was an E and the pile splits thing? That analogy no longer works. Because when you have link functions and distributions in which there is no residual variance, that residual variance cannot change as a function of what you do to the model. So do you remember the number, the arbitrary number that we said residual variance is going to be at level 1 if you're using a logistic model? It's totally arbitrary, but it comes from the logistic distribution. What's residual variance? It's in your notes. Find it. I'll show you where it is. This one. The idea of this Y star thing. Y star is the logit. It's the continuous thing your model is actually trying to predict. Some people talk about it as a latent variable, but it doesn't exist. It's just a transformation of the predicted. 3.29 is the magic number that describes residual variance if you're using a model. What happens if you put together a really super good model that should have explained like 80% of the variance? What's it going to be? 80% less? Nope, 3.29. No matter how good, it's 3.29. So what happens in these models is that the variance actually increases when you add random effects, because it's trying to figure out what the variance of the model would have been prior to adding all the stuff in. So 3.29 can't go down. So no matter what we do, let me find this thing again here, 30, here we are. No matter what we do, that number is going to stay constant. What if I picked probit instead? What does that number become instead of 3.29? I'll give you a synonym. It's unit. 1 becomes 1 in probit, but it's a fixed number. So what happens is that the coefficients change scale across models as you explain variance, but the variance can't go down. So when you're comparing results across models, you have to remember that and not interpret them as some kind of indication of the relative contribution. So if you put in a fixed effect and it's significant, and then you put in another fixed effect, say at level 1, and it's significant, the first fixed effect is going to get bigger because it's rescaled according to your new total variance. The easiest way that I can describe this is with an analogy. Like that shirt, they're like, it's $300. Oh, well, that's in Logits. So I go over to the little machine, right? They have your price scanner, which I refer to as my inverse link function, and I beep it, and it tells me what in actual dollars I will pay prior to all of my discounts, right, and everything that you get. And so pretend like that you're the manager at Kohl's, right, and everything's always on sale. And let's say that to make ends meet on a particular shirt, like one of the really nice ones, like you got to get $25 for it or you're going to go in the hole. That's your bottom line. So what do? You start off with a 50% off sale. You put 50 Logits on the price tag because then they're going to get 50% off and pay $25. Well, what if it doesn't work? You're stuck with a bunch of these shirts, but you got to get rid of them. Well, all right, I'm going to change the tag and say that it's a 75% off of 100 Logits to begin with, and now it's only $25. The idea that you're rescaling what it used to be instead of what it is now, like that's how these models work. Once you explain variance, it's like, well, it can't go down, so I got to figure out like what it would had to have been to now only be 3.29. And so it's like all the coefficients are like predicting the regular price. That's the best way I can explain it. I just want to point this out to you because what's going to happen is that things are going up, not down. And it looks confusing if you're not aware that this is going to happen. So just think of it as you're shopping at Kohl's and everything is scaled relative to some original price that actually doesn't matter, because at the end of the day, all you're going to pay is what you're going to pay at the register, 3.29. So how's that? And that's my Kohl's analogy. I don't know of any other store that has chronic sales so frequently. I don't think there's a single thing in the store that's actually the price it is on the tag. Another thing that you're going to find here, REML has gone away. There is no such thing as REML for these models, not with likelihood. So on the plus side, that means that any kind of nested model comparison you want to do with likelihood, go right ahead. It's all fine. On the minus side, what was good about REML? Why did I make us use it most of the time? Small samples. Why is REML good for small samples? In ML, random effect variances become downwardly biased, too small in small samples. In REML, they're accurate. So that means that small samples don't get a REML advantage with these models They only get ML. So accuracy can be a problem if you don't have a lot of data. So here's what an empty model would look like, say, for a binary outcome. I'm using the same notation. There's only two differences. Number one, I'm predicting the logit as the outcome rather than the original outcome so that I can use a linear model. Beta 0I is my placeholder. So let's say this is longitudinal data. What's normally there in an empty model that is not there at level 1? What's normally in my empty model at level 1 that's not there? Residual. It's not that the model's perfect. It's that residual variance is a determined quantity. We know what it has to be because it changes as a function of the mean. So if your predicted probability is 0.5, the variance around it is 0.25. If your predicted probability is 0.9, the variance around it is 0.9 times 0.1. It shrinks as you move towards the extremes. People calculate intraclass correlations on the model scale using 3.29 for the residual variance. This is a little squishy. I wouldn't put as much stock in these intraclass correlations as I would with the general models because 3.29 can't really be accurate. Not on the data scale. It's a model-based quantity. So it's accurate in the sense of logits, but it's not a direct conversion to probability. Interestingly, I have not seen much treatment of how to do intraclass correlations using other kinds of generalized models. As an example of this, I've seen several places that just stick a 1 in for the residual variance for count models. And Walt Stroop, his book, that's the one I was reading on vacation, told you about last time. He's in the stats department at the University of Nebraska, so after the book came out and I tried to read it, I asked if I could meet with him, and I had like my list of questions, right? Here's all the things I didn't understand that since you're stating in front of me, I want you to explain. And that was one of them. I said, where'd the 1 come from? He said, well, I got it from this other book. So I checked that book out of the library, and it had a 1. And I was like, where that came from? I'm going to email the guy. Emailed the guy. He was nice enough to explain that he said, I don't know where that came from, but I don't think it's right. That was his response. So I greatly appreciated that he actually responded to my email, but I don't know where the 1 came from. It's just one of those things that just like, it's like telephone. Like somebody said something and it got translated into 1. So intraclass correlation is not as important. It's subject to debate as to how to make them. In models where the mean and the variance are dependent, I think it needs to change as a function of, I think it should be a quantity that is not actually 1 number. Like I said, I've seen inconsistent treatment of how to do that. So, it's one of those things. If we had a random linear time model, it would look like this. It looks exactly the same, just minus the E. So the linear predictor part, the idea of putting fixed and random effects in the model, that's all the same. The only catch is what they're predicting directly is this logit quantity rather than the probability. All right, that's ordinal. We'll get to that later on. One other complication. Do you remember how I used to talk about the fixed effects as what's going on average? Like the fixed intercept is the mean intercept, and then random is how far off yours is, and the fixed slope is the mean slope, and random is how far off yours is? Not anymore. So this is a distinction that did not exist for general models that exists for generalized, and it has to do with the severity of each person. So we have to add that interpretation onto the fixed effects and think of them still as middle, but not mean exactly. All right, so we talked about this briefly, change in scale. There's a paper that I gave you that talks about this in more with a grain of salt. So here's the descriptive statistics. I'm going to be using SAS Glimix. I threw in a Stata ME logit code that goes with this, And on the very last model, I also have this in M+. So I'm starting to show you what it looks like in other packages as well, because I don't have any of these models on the Piles of Variance website. So everything for the book, I already have all of the examples worked out in these things, but not for these. So I wanted to give you a few more resources. So here is the mean of the free lunch variable, 0.3075. That is the proportion of students who get free or reduced lunch. So that's my conditional mean to be predicted. How does that number wiggle around as a function of math scores? At school level, if I were to calculate the average for each school in terms of what proportion of their kids get free lunch, it ranges from 0 up to 80%. So there is a whole lot of variation between schools in free lunch, even though the variance here is entirely determined by this mean. So I am using group mean centering. I had previously calculated school mean math. So I'm creating within school math as math minus school mean math, and school mean math centered at 50, and I'm dividing these coefficients by 10 so that the scale of these fixed effects is a little bit bigger. So we'll talk about a 1-unit change as a 10-point change in this example. But you've seen before, no CL print shuts off the listing of every unit on the class statement. Name-lent keeps it from truncating the names of your fixed effects. Now this is the new one. These two here. Method equals. We used to have this in mixed and it was ML or REML. In Glimix there's a lot more choices. The default in Glimix is pseudo-likelihood. That's the not good. We haven't talked about that much yet, but it's the not good kind. So I am asking it to do adaptive Gaussian quadrature instead. That's a mouthful, isn't it? That's what quad stands for. It's true ML. We'll talk more about that in a little bit, but just wanted to point that out. And quadrature points is an option that you can specify, or you can let the program figure out how many it thinks it needs. Letting the program figure it out is probably best, but I specified it here so that my answers would be the same across the 3 packages I'm doing for these models, Stata, M+, and SAS. That's why I put that in. And then last but not least, this thing. Gradient is a troubleshooting option. I always put it on these models. Does anybody remember what that word means? We haven't talked about it much. The gradient is the partial first derivative with respect to each parameter. In English, that thing tells you how at the top of the likelihood each parameter's estimate really is. If it's really at the top, the slope should be 0. So you want the column that's going to be called gradient to be filled with zeros as far as the eye can see. And if you get values that are approaching not 0, those are the things that it's having trouble estimating. So those are troubleshooting tips, things to watch for as gradients that become not 0. Model is the same as before. You list your DV here. Now here is an option that I've added. Can you guess? Yep. Identity link. Remember what that means? Times 1? Yeah. Meaning leave it alone and normal. Glimix defaults to mixed. Isn't that funny? I find it funny. So those are the options that we will pick to set it up to be something else. So for binary data, we're picking binary distribution and logit. For illustrative purposes, I am asking it to estimate. And you're like, doesn't that show up already, Lesa? Yes, it does. But here's the magic. iLink. That's my little price scanner. It converts logits to probabilities for you. Do you know what ILink stands for? Inverse link, yeah. Or what I would call unlogit, or backtrade. Any of those I would accept, but ILink is the faster. The analog to that in Stata is NLCom as opposed to LINCOM, and you have to go into the Stata archives to try and figure out what it calls the intercept, which happens to be this. So I'm writing out the same thing that ILink is here. So we're predicting a binary outcome with no random effects and no residual variance because binary outcomes don't have one. You'll get a message that says that your convergence criterion is satisfied. That's always good. And here's -2 log likelihood. This is the same as before, meaning, is that number good? 16,145, is that good? Your answer should be, It has meaning only relative to other models for the same data, and only for the exact same cases. The log likelihood is literally the sum across cases, so it has to be the same cases for that number to mean something. And in this case, what do I have in my model? I have a fixed intercept only, meaning that I am allowing the mean proportion of people who get free lunch to be something other than 50-50. So this is the worst possible model I could ever fit for these data. So from here, that -2 log likelihood will get bigger or smaller as I add stuff. Smaller. This is deviance. This is badness of fit. So it should go down as I add stuff. The rest of these are things that also show up in mixed. Here is something that shows up for certain outcomes. This is going to become an index of over-dispersion when we get to outcomes for which that is possible. Those include counts and binomials, so we'll talk about those later. But for now, these will just stay 1, and everything will be happy. So here is the one parameter that I estimated. I have a fixed intercept of -8,117. And you're like, aren't we predicting the probability of something? Can I have a negative probability? No, but can I have a negative, what's 0.8? What's that thing? That's a logit. That is the log odds of the probability of a 1. So when I inverse link -0.8, there's my formula. This is the probability of a 1, which is not the default. So here, then, this t-value and p-value. Note p is not the last column anymore. It moved. Gradient is now the last column. That logit of -0.8 is significant. Is that a yay or a who cares? What does that mean? It's testing the parameter against 0. What's the logit of 0? Probability of 0.5. So yeah, this is telling me that my mean of 0.3075 is not 0.5. If I was interested in whether something was due to chance, maybe that would be interesting to report that it's not 0.5, but that's what it means. Gradient then, 2.155 e to the -9. That's scientific notation. What does e to the -9 mean? I think it means move your decimal over like 9 places before you get a number, something like that. Yeah. Or 9 digits after the decimal is when your numbers start. That means good. What do we want gradients to be? 0. So this is 0 to the 9th decimal place. Yay. So here's my estimate statement. I estimated the intercept, which is showing up right here, and then here's the part that I did it for, that right there, mean. Isn't that helpful? Mean what? That means probability. It's another instance of SAS labeling things in a way that you have to have job security once you figure it out. Mean. Ugh. Because everything that we estimate is going to be called mean. This happens to be the mean, but we're going to estimate slopes, and they can get called mean too. So there. It figured out my probability, and it gave me a standard error for it, which is nice. Because then I could use that information to put in a plot to make this model more understandable. Okay, with me so far? Now let's make it a multi-level model. Empty means two-level logistic model predicting paid versus free lunch. Here's my equation. I'm adding U0S. Note my subscripts here. I'm done with IJ. You remember me getting mad about IJ? Individuals within groups spelled wrong? No, I'm KS. You know why? Because these are kids in schools, damn it. You can do that. People don't do that, but you can. It makes your code easier to understand in your equations if you use letters that actually mean something. These are kids in schools. So everything looks the same up to here. This one's new too, excuse me. By the way, I had a couple of you ask me the same question, troubleshooting previous homeworks. If you forget this class statement with the school ID variable, for whatever reason, that makes it run way slower and sometimes not even converge. I think it has something to do with it sorts the data for you when you put that in there. It has something to do with sorting, but that's why it's there. So even though class is not technically being used by the model, it's being used to identify the nesting variables, so don't forget that. We've added this. Random intercept, type equals UN, forever and ever, amen, subject equals school, same as before. Now, actually, ODS output. I have macros that do pseudo R-square in Glimix as well. They're up on my web page. I put them up, by the way, a while back. Lesa's MLM macros are right here, all the ones that I have. I have a fit test one in Glimix, and I also have a pseudo R-square one in Glimix. So that saves that. Now here's something new. Cope test. This is an option that was red, meaning it was experimental for a long time, and it's now blue. It does likelihood ratio test for you. When I found out that this existed, I was like, holy shit, we're going to do everything in Glimix from now on so I can use this. And then I put together an example in which it got it wrong. And I just reran that same example, and it's still wrong. So you can use it. I don't know why it would get it wrong sometimes and not others, but I have seen it happen. So that's why I don't use Glimix for everything, even though it does likelihood ratio tests for you. The notation for this is you have to tell it what you want your G matrix to look like. So you're going to set some parameters to 0, and the things that you want it to leave estimated are going to be represented by dots. So this line right here with my comment, random school intercept with 0 means estimate the model without it, do a likelihood test relative to this model. So the model that we just did is what it's going to estimate to do a comparison by adding previous model, but we didn't have one because residual variance is 3.29 the end. Now the only thing that shows up is UN11. What's that thing right there? Random intercept. And what does 11 mean? as opposed to 2, 2, or 3, 3, or other numbers? It's the location in what? Which covariance matrix? G, yes. This is row 1, column 1 of the G matrix, which is unstructured, and that's why it's un-1-1. It always goes in the order in which you list them. So my random intercept variance is 1.9. Here's my gradient. There's numbers in it. It's pretty close to 0, but it's heading towards not 0. If I use that 3.29 value to replace my level 1 residual variance, then in the logit scale, right, what's the fixed intercept supposed to be in an empty model? What does it represent? What did it used to represent? Let's put it that way. If you know nothing else about a case, your best guess for their outcome is the mean, right? And that's what it was before. The mean was 0.3075, which was the mean of the variable, right? Now it's telling me is 0.275 that does not have a random intercept in it, which is the one we just estimated, and it's testing the difference against the current model. It's telling me how many degrees of freedom it's using, so it's doing your answers for you. And then it's doing the likelihood ratio test. Note MI. You're like, what does that mean? P-value based on a mixture of chi-squares. So that's the thing that I told you about that I just can't care about. I don't have room in my head to care. That's why there's a tilde everywhere in my book for degrees of freedom. This is the idea that variances can't be negative. And so what you really should be doing to do your likelihood ratio test for variances is comparing it to a mixture of chi-squares, where it would have been negative is a chi-square with degrees of freedom 0, and where it would have been positive is degrees of freedom 1. So it's actually computing a p-value based on a mixture chi-square distribution for you. So it is more accurate in these cases. Now, a chi-square of 2,973. Do you know what the difference is for a mixture critical chi-square versus a regular one for 1 degree of freedom? Anybody memorize chi-square tables? No? Just at my house? Yeah. I'll have Huey memorize those as soon as he's done counting to 20. Right now there's a few holes in going. He likes to say 12 a lot. Anyway, 1 degree of freedom is 3.84. For a mixture chi-square that it's using, it's 2.71 instead. So the fact that our minus 2 log likelihood difference is like 3,000 means who cares? You should care if it's between 2.7 and 3.8. So here then is the rest of the story. I can calculate a random effects confidence interval to describe this variance the same as usual. So if I use the fixed effect as the middle, and I use the random variance around it from my random intercept, let's see, it's 1.9, yep, 1.9545. In logits, it's this, and in probability, it's this. Now, those numbers look awfully familiar because that's pretty much what the raw data said. Somewhere between 0 and 0.8 was the raw data in terms of your proportion students who got free lunch, and that's what my interval's predicting. So it's right on top of the data, which is always comforting. So let's add some predictors. First off, I'm adding a fixed effect of school mean student math. So this is just like in your homework where you would have group mean whatever as a level 2 predictor. So school mean math centered at 50 is my predictor here. I am writing out estimate statements to try and demonstrate the importance of order of operations when you're going to do inverse linking. So I'm asking for predicted outcomes for 3 different levels of my predictor of math, as well as I'm trying to unlink a slope to to show you what happens when we do that. I'm also going to do square. Changed its value once more. Minus 1.4. That's the predicted logit of getting free lunch for a student in a school with average math. So the school mean math is 50. What happens to the predicted logit of getting a free lunch as math increases is that it goes down. So long as we keep logit in the sentence, we can talk about this the same way we would any fixed slope. For every 1 unit change in school math, which in this case is a 10-point difference, the logit goes down by 1.44. Yes, yeah. Guess what I'm going to do with it? Nothing! I hate them, but this is an odds ratio. So, there you are. So the rest of the output here, then, I want to use to point out a common thing that people screw up when they're trying to interpret these models. Get everything on the screen here at the same time that I want. Okay. So, here are my estimate statements. The estimate is in logits. So these are the predicted logits at each of these levels at math. So you'll see the one in the middle at 50 is exactly the fixed intercept from above, as it should be. Each of these units differs by the slope. So a 1 unit change in math has an equal difference in predicted logits. From here to here. From 49 to 50, from 50 to 51, the distance is the same in terms of logits. It's a linear effect of school math. If I back translate those predicted logits, if I take the inverse link, that's what mean over here is doing for me. So if I'm in a school with average math of 50, the probability of getting free lunch for any kid in that school is 0.18. If I go 1 unit up in math, that probability drops to 0.05. If I go 1 unit down in math, that probability increases to 0.49. 0.49 to 0.18 to 0.05. Those intervals are not the same. An equal distance in slope for logits does not translate into an equal distance for probabilities. The difference in probability has to get smaller and smaller the further out you go, closer to 0 or closer to 1. It has to shut off. So when you are talking about your model, the slopes hold in logits only. They do not hold in probabilities. So if you want to talk about a 1 unit change, it's a 1 unit change in the logit. But what a 1 unit difference is changes as a function of where you are on the probability scale. It has the biggest effect if your predicted probability is around 0.5, and it necessarily has to shrink as it gets closer to 0 or 1. So there's a picture in the lecture that I like. I stole it from Snyder's and Bosker's Multilevel book, in fact. Let me find it again because I think it helps clarify this non-intervalness. It's this one right here. The top is probability and the bottom is logits. So if you think about a 1 unit difference, right, going from a predicted logit of 0 to 1 is going from a predicted probability of 0.5 to 0.73. But then going from a logit of 1 to 2, still 1 unit, is now a lesser difference in probability of 0.73 to 0.88. And 1 more unit of logit only gets you another 7% increase in probability. So when you talk about slopes, it has to be in logits or it doesn't make any sense. What you can do to make it more interpretable, though, is unlogit back translate, inverse link the prediction. So once you've used your slope in logits to get a predicted y, you unlogit that predicted y to turn that into a probability. But you cannot unlogit a slope, even though SAS will do it for you. Yet another instance of job security. So the slope itself is minus 1.44. That is the change in the log odds per change in math. Even though I could take that number and convert it into a probability of 0.19, that means nothing, because you don't get a difference of 0.19 in your probability per unit math. It doesn't work that way. So we never unlogit slopes. We always unlogit predictions made by slopes. So in the figure that I am eventually going to show you that goes with this example, what I do is compute a predicted outcome from the model in logits, the same way as usual. We'll have our fixed intercept plus slope times variable plus slope times variable and so on. That gives me a predicted logit. I can then take that predicted logit and back translate it into a probability. So there's an order of operations here. You can only unlogit predicted outcomes, never the slopes that create the predicted outcomes. So where we're going to end up then are predictions of lines that are straight lines when it comes to logits, but they turn into bendy lines when it comes to probability. So we'll see that when we get all the way through the example. Okay. Do you want to hear any of that again? I don't like odds ratios because I can't handle the idea that your coefficients get multiplied together rather than added. It just makes no sense to me that you would do that. Handle it. That being said, a lot of people like odd ratios as an effect size in these models, because to people who don't hate the idea that you have an odds of 0.8 would mean something. I know that that means it's a negative slope because it's under 1, but other than that, I don't have an intuitive sense of what that means. I'm sorry, I don't. But there's how to get one if you'd like one. So yes, we will use the model to predict logits. Model coefficients are in logits. That's my logit intercept, and that is a slope that predicts logit. If you want to take that and make it understandable, you take the predictions of the model and unlogit them. But we cannot directly unlogit